speed. So
Distance over time.
anyway, let me just rephrase that last comment I was making. So velocity is positive or negative, but when I talk about the speed, what's your average speed from home to school? You're always going to say, oh, my average speed was 35 miles per hour or 40 miles per hour. Or going home, you would also say, well, my average speed is 40 miles per hour, whatever it might be. Okay, so when we talk about average speed, we need to have a starting point and an ending point, right? Okay, because it's over a time interval. So I'm saying you start from home at 7:30 in the morning, and you get to school at 7:50. So that was a time interval of 20 minutes, right? And your starting point, you would think, so that's like your initial. So this is like your, this is your start time, and this is your end time. So if you look at f of t, we think of f of t as like your end position. And right here is your starting position. So if, let's say, you lived 10 miles away from school, and it took you 20 minutes to get there, you could figure out your average speed based on that. Now keep in mind, your average speed, you know, so maybe you're driving some side streets, sometime you're on the freeway, you're at stoplights, so you have to incorporate all of that into that average speed. Okay, let's look at an example. So an object is dropped from rest at the top of a tall building, falls at y equals 16t squared. Now, notice that I gave it a positive 16t squared. If I were referring to the velocity, just kind of a side note, it would be negative, because when you drop something, it's falling, it's going into the negative direction.
Would you consider you're good at physics?
Moving on.
I'm just asking. No, I'm really just asking because physics has like everything to do with.
I have not taken physics. I didn't take physics in college. I took it in high school and I really liked it, but then again, I like math, and math, physics are very closely related.
Math is physics.
I guess you could say I was good at physics, but I don't know. I haven't done it in a long time.
Physics needs to die.
Wow, that's so good.
Oh my God.
Restart.
It's fine to say he doesn't like physics.
I love physics.
Guys.
Yay.
It's just like, this is the real deal.
Moving on. We're going to find this average speed. Shh, guys, really? So, my t sub 1 is going to be 0, and my t sub 2 is 2. So whenever I ask for the first 2 seconds, my starting time is 0. Make sense? Okay, first 2 seconds, so I want starting from 0, ending at 2 seconds. What is the average speed? Now, it says delta y over delta t. Basically what we're looking at here is slope, but it's not slope of a straight line, it's slope of this curve. This is 16t squared. This is a parabola, right? A t squared or an x squared looks like a parabola. So we're going to plug in, again, if y equals 16t squared, we can think of this as f of t equals 16t squared. Just think of it as a note, like in function notation. So we have f of 2 minus f of 0 over 2 minus 0. So we have 16 times 2 squared minus 16 times 0 squared. I'm just plugging it in. Okay, so I'm plugging in those time values into the function. Well, 16, so this is going to be 16 times 4, so we get 64 minus 0 over 2. So we should get 32. Speed and velocity are length of the, like the unit measure, which in this case was feet, and second. So we have 32 feet per second. So again, the ball is dropping, so the average speed over the 2 seconds of the ball is 32 feet per second. Questions? Okay with that? Fine. Now, that was an average speed. So what would we do if we wanted to look at the speed at exactly 2 seconds.
Instantaneous.
Instantaneous speed is what we're looking for. So we want specifically right at 2 seconds. Well, we could figure out the average speed by finding out, right, the slope of the 2 points. But now we want to do it with just 1 point. Okay, so basically what we have to do is we're going to say, let's say we're going to do the same thing from 2 seconds to any slightly later time, 2 plus h. Okay? H could be anything. H could be a second later. It could be half a second later, a quarter of a second, 0.1 second later. H is just going to be a variable for right now. We're going from 2 seconds to 2 plus h, some slightly later time. So we're going to plug into that same formula. Okay? So we're going to plug in f of 2 plus h minus f of 2 all over 2 plus h minus 2. Remember, think of the 2 plus h, that's t sub 2, and this is t sub 1. Right, so I'm still kind of plugging into that same formula, the f of t sub 2 minus f of t sub 1. Well, what's that look like? Well, I have to plug in h plus 2 into t. So that's going to look like this.
Wait, where's the T? How do you know F is 16?
Oh, you're using the same.
I'm using the same formula. We're still working on the same problem. But the first part A was the average speed during the first 2 seconds. Now I want to kind of zero in, if you will, on just what's happening at 2 seconds. Good? So remember, my f of t was still 16t squared. That's where I'm getting the 16 times what's in, remember, whatever's in parentheses, that's what we're substituting in. And then in the bottom,
Will the variable always cancel out?
so that's important to note. We're not going to cancel it out just yet.
Well, yeah, you can solve it.
Okay, I'm going to explain that too. So it looks worse than it is. Just FOIL this out and multiply it. It's not so bad. It's 4 plus 4h plus h squared, and then minus 64. In the bottom, we just get h, right? The 2's cancel. Okay, we're okay. I'm just distributing now. Okay. So we can see at this point the 64's cancel. And notice in the numerator I have h in both terms. I have a 64h plus an h squared. And I have an h in the denominator. So I'm going to factor out h.
Can you factor out 16?
Oops.
Can you just cross out every
You could factor out that too, but I'm really focused on the h because that's what I have in denominator. So if you wanted to, you could factor out the 16 also. But I'm just going to, so I have 16h. What do you think? Do you think we can cancel out those h's?
Yeah,
The answer is yes, we can, but there's a reason for it.
because it's in every single term.
Well-
it's multiplication
All right.
over
Okay.
division.
We can cancel because h is not equal to 0. Think about that for a minute. We can't have 0 in the denominator, right? But I already told you that this was a slightly later time, so that means h has to have some value, right, other than 0. Like I said, it could be 0.1, 0.01. So that's why we're able to cancel. So that means our answer is 64 plus 16h feet per second.
What's h?
We'll look at the next, it carries over to the next page. We'll get there. We're good so far?
Yeah.
Okay, so we can do on we could go into our table of values for this function. Right, we could go into the table and put in values. Now remember, what did I say? H is a slightly later time. So here, so if H was 1 second after 2 seconds, so in other words, from 2 to 3 seconds, the average speed is 80. This would be 2 to 2.1 seconds. The average speed is 65.6. At 2 to 2.01 seconds, the average speed is 64.116. So as your slightly later time gets smaller and smaller and smaller, what's my average speed approaching? 64. That's a limit. What we just did was a practical application of a limit. We said, oops. So as H approaches 0, right? The average, or actually not average. Okay. So the speed is approaching 64 feet per second. Okay? Questions?
Yeah.
Yeah, no.
I'm confused when you say 2 to 0.1.
Oh, so remember H is a slightly later time. So remember how I had from 2 to 2 plus H? So this would be 2 to 3 seconds. This would be 2 to 2.1 seconds, 2 to 2.01 seconds. So I'm saying that basically these are my H values. So I'm looking at from 2 seconds to 2 plus whatever this column is.
Does that have to do with the page before it?
Yeah, that's what I couldn't fit it all onto one page. No?
Oh.
Matthew?
So, on the other page, you said.
On the other page.
64 plus 16H. If we said H
Right.
is 0, you would get.
Right, so, okay, remember the previous page, we said the average speed, or we said the speed, right, we wanted to look at the speed at 2 seconds, so we looked at from 2 to 2 plus H seconds, which that came out to this, 64 plus 16H. So think about, as H is getting smaller and smaller and smaller, what's happening to this value? As H gets closer to 0, this is going to become 0, right? And so we get 64 as our limit. It,
Slightly.
like, okay, well,
I get the 0 part, but I don't get the 0 because it has to be 2.000. How close it's a 0 when you start with.
okay, so when we talk about limits, right? Limits, we can look at limits graphically, we can look at them on a table of values, or kind of theoretically, as H is getting closer and closer to 0, that whole 16H is going to get closer and closer to 0. So really our value is approaching 64. Okay, so this is the formal definition of a limit. Don't worry about it so much, just that basically as we get closer to an X value, this gets closer to a Y value. We call this the epsilon delta definition of limit. This would be something, if you take calculus in college, you might encounter. Basically, what I want you to remember is that the limits are Y values, okay? And obviously, what you're approaching, that's your X value. So you're looking on a graph at what's happening close to a particular value, and we want to know what the limit is. We look at the Y value on there.
Oh, there's Greek. I can't read Greek.
Yes, it's epsilon delta. It's basically epsilon. This is epsilon and this is delta, lowercase epsilon.
Epsilon is when you.
Yes, it is.
I thought it was a logical.
I just said it's lowercase delta. So
Epsilon is when you
the
get
delta.
zero, right?
What's wrong?
That's not what the fraternity look like.
There's uppercase and lowercase. So they're used in different areas. Yes.
That's cool. Fraternities use uppercase.
Surprise. Okay. Basically, we're saying as x, so epsilon and delta represent very, very small numbers. So as x is getting really, really small, then the y is getting closer and closer to something. That's all this represents. It's just saying it's getting closer and we're like zeroing in on a particular place in the graph. Okay, let's look at this graph. Sine x over x on our calculator. So go ahead, in your y equals, we have sine x. Make sure that you're in radians. And then let's do zoom trig number 7. Okay.
What's the y equals again?
It's sine x over x. So plug that into your calculator. Sine x over x. Okay, now, if you look in your notes, right, it says sine x over x. Now, 0, we can't plug in 0. It's undefined at 0. In fact, if you went to your table
The limit is 0.
and you tried to plug in 0, you would get an error. Now, when we plug in 0, you get an error, but we could look at values that are really close to 0. So, for example, I could plug in 0.1. I could plug in 0.01 and 0.001. And then I can plug in negative 0.1 and negative 0.01. Oops, that wasn't supposed to happen.
When you plugged in 1, you got it. I mean, when you plugged in 0.0.
Okay, so I'll explain that. When
What would happen if you plugged in 0.0001? I just see that.
that would 0.0001.
That'd be over 1. Oh, awesome.
Okay, so what happens on your calculator, and this is something I've been telling you, especially when we had like asymptotes and things like that, your calculator will only round so many 9s, and then it's just going to make it into a 1. But we know right at 0, it's not equal to 1. You get an error. Okay, there's like a hole in the graph or something.
Not equal to something at 0?
It's not equal to something at 0.
How come?
So, because if you tried to plug in 0, we would get undefined in the bottom. Okay?
I don't really understand this all, but I think
So we just looked at the y values as x approaches 0 from both sides. Did I do the z box with you guys also?
Yeah.
Did I do the z box?
Very-
The zoom box,
Zoom box.
number
Yeah,
1?
we did it.
So I can also look at making a box right around remember, you have to press enter, and then you can just kind of drag it down.
I've never learned this.
What?
It's so cool.
Wait,
So-
what did you just do?
Press Z, number 1, box. And then you can move the cursor to, usually I like to work from the upper left-hand corner. Click enter, or press enter, and then drag it down and over with your arrows. And then
Yeah, what?
zoom, number 1.
Oh, zoom 1. Why didn't you just?
So what that does for you is it allows you to zoom into just one really small picture. Remember, I'm looking at values closer and closer to 0, x equals 0. So I can do this. Did you make the little box around it?
Which box do I do?
Move the cursor to the top left.
Oh, that's really cool.
Isn't that cool? So
That's so cool.
Why were we not told about this before?
Oh, I did it.
Wait, this is not
Ah.
working.
Is this it?
Did you zoom? Okay, so you should get just like a closer view of what's happening. Now notice my x value that popped up here was 0.0327. Now,
Wait, I don't know what happened.
Yeah, just keep saying error.
if you press trace,
Fixed it. You put on plot 1 and plot 3.
what's wrong?
I took that out. I changed that around already. Yeah, this is not working for me.
You got it.
That's rough.
Now if you press trace,
You're the best, Alex.
Trace.
if you press trace, it automatically puts your cursor onto the curve. So look at your values here. Yeah, you got to make it good. So now you could do the zoom box a number of times, but honestly, one time I think gives you a pretty good glimpse of what's happening when you get really close to an x value of 0. What's your y value look like? It's 1. So therefore, the limit is 1.
Wait, how do you figure that out?
What did Mr. Chabot say about the limit last time?
Memorize that. It's 1.
Oh, yeah, that's.
What happened? Did you get it? Press trace. Press trace. And now get it as close to the y-axis as possible. And what's your x and your y value? There you go.
Okay, so we'll never hit 1. Yeah, because y value is next.
Why can't physics be consistent? The world's never know. So the limit is
Okay, moving along.
the limit is the y value.
The limit is the y value. Always remember that. So now let's look at the graphs at the bottom. My guys. Okay, next I want to look at the same limit but with different graphs. Okay? Now remember, on that graph, did you notice I kind of looked at from the left and the right when I did the table? Like I look at some negative values and some positive values. Okay? The important part is, from the left and the right, we want them to be the same. So here are 3 examples of 3 different functions that have the exact same limit. So from the left, it's approaching a y value. Enough with the food, guys. Okay, from the left, our y value is approaching 2. From the right, it's also approaching a value of 2. Notice there's a hole in the graph. This is something that we'll learn about later called a removable discontinuity. But it doesn't matter if there's a hole in the graph. Is it approaching the same value from the left and the right?
Yes.
Yes. So if you look directly over the y value, that is my limit. Okay, so my limit here is 2. Look at the next graph. So again, from the left is approaching 2. From the right is approaching 2. This has no effect on the limit.
What is that?
It's just it's a removable point, so they just put a point somewhere else on the graph. But we don't care. We don't care if there's a point there or not. What we're really looking at is just on the graph, what's it getting closer and closer to?
2.
And then this one has an actual value.
So there's no
So there's no hole in the graph, but the limit is still 2. Okay, so what's the question? What I'm basically telling you is that it doesn't matter if we have a value at a particular point or not. Like that sine x over x. Sine x over x, we looked at that example. There was an error when we looked at 0, right? But that didn't matter. From the left and the right, it was getting closer and closer to 1, so that was our limit. This example here, this didn't have a value, but our limit was still 2. This one didn't have a value here, but it had a value somewhere else. But again, it didn't affect the limit, because when I was looking at from the left and right, it was still approaching the same value. And this one actually has a value, so this is actually the easiest one. When it has a value, it just ends up being.
So there are no limits on that one.
Okay, when it has an exact value, the limit is that value.
Will that only come up with 1 point, or if there were 2 points, would that there be 2 limits?
You mean if there's another point below it? It wouldn't be a function, so we wouldn't worry about it. Okay, let's look at, there's 2 properties of limits I want to look at here. One is the limit of a constant, and then one is the limit of the identity function. So these are like the most basic properties here. The limit, here, this. The limit as x approaches c of k is equal to k. Think about this for a minute. Let's look at this example. The limit as x approaches 2 of 3. Whatever comes right here, picture that's a graph of something. What is that the graph of? Y equals 3. So 1, 2, 3. Right, here's my line. Here's y equals 3. So if I'm looking at the graph as I get closer and closer to 2, what's my y value? 3. What if I said the limit as x approaches 1,000 of 3? It would be 3. What if I said x approaches pi of 3?
3.
The limit is 3.
It doesn't matter what we're approaching. If this is a constant, that's your answer. Because it's a word, is the y value ever changing? No, it's staying 3. So that limit is always going to be that constant value. This, it's kind of like, doesn't matter what that is. That 2 is irrelevant. It could be any number. If this is a constant, that's your limit. Next one. What about, this is, picture the line y equals x. The line y equals x looks like this, right? So at 3, what's the y value approaching? 3. It's called the identity function for a reason, right? Whatever the x identity is, that's the y. X and y are always the same along this line. So if I had the limit of x as x approaches 5, it would be 5. Okay?
Wait, can you, one second.
I'm gonna ask a really dumb question here, and I hate to
No, there's no dumb questions.
There's no dumb question.
There are dumb people, but no dumb questions.
Alright, I hate to be a dumb person sometimes.
Don't pick
What's your question? Just go for it.
I don't understand what a limit is.
I was your fence or did.
Okay.
That's a good question.
Serious question. What does it limit?
What is a limit?
I'll play later.
Okay, I'm just going to go back here really. Oops, went too far. Right here.
Shut up, Missy.
The limit is a y value that my graph is getting closer and closer to.
But it never can touch it.
It could touch, it doesn't have to.
Well, how can I touch if it's a limit though?
Why is there limits?
Why is there infinities?
Okay, the
They're
limit.
just A's.
Sometimes, what I'm trying to explain to you that a limit doesn't care what's happening at the actual point. Okay? That's why I showed you the previous graph where there were holes in the graph, and then one where there wasn't, but it didn't matter. The limit, the y value that you're getting closer and closer to, that's all we care about.
But if you're getting closer and closer to it, you're touching it, so.
Yeah, and that's fine. That's fine. It's okay to touch it.
But then how is it a limit if you're touching it?
It can only get to there, but it
can't
can
go
touch
past
it.
it.
Let's just
but
say it could
stops there.
get closer and closer to it,
You can
or
touch
ac-
it, you can't exceed it though.
you can.
If your limit is 3, you can't get to 3.1.
Right. Okay. So here's an example. Here we're getting closer to 3, right? From the left and from the right. Honestly, I don't care if there's a value right there at 3. The limit. So what I'm saying is, from the left and the right, I'm still getting closer and closer to a specific y value, and that is 3.
Wouldn't you also be getting closer and closer to like 1, 2?
Well, that would be if I was approaching 1 or 2. Again, what I'm saying is it doesn't matter if it has a value there. We're just looking at what happens if you get closer and closer to it. It's kind of like it's irrelevant if it has a value there or not. That's basically what I'm telling you. That it could be that exact point, but this could be a hole in the graph.
So it's just the visual.
Okay, just kind of bear with me here. I will just explain, with limits, basically this is saying you can distribute a limit through a plus sign, through a minus sign, multiplication. It's almost better to look at the examples.
Let's just not discriminate.
And from that day on, it sure would never understood that.
So let's look at here. This first one is pi is a constant, so the limit is pi.
This part's understood. This part's easy.
Remember,
Y equals 5.
yeah, this is the graph of y equals pi. So imagine 1, 2, 3, 4. So here's my line, y equals pi. That's supposed to be straight. But it's a horizontal line, right? So what y value am I getting closer and closer to? Pi. The square root of 2 here?
It's Friday.
Excuse. Square root of 2. All right, guys. Do I really need to keep a seating chart or something?
No.
Guys are worse than my ninth graders today. All right. Next one. Okay, this one is kind of, it's almost.
Yes, that's the one.
Basically, I'm just going to plug in A.
So 2a squared minus 5a plus 3.
Right.
That is so.
Now, what I'm going to explain on the next page has to do with polynomials. So, polynomials. Okay, so a polynomial function just means we have whole number exponents, right? Something like x to the third plus 2x plus 4, something like this. Here's x squared plus 3x minus 4. Polynomials are the easiest problems to find the limits of because you just plug in.
I need to bring the hotness down because I'm.
A is 4.
So the reason we can just plug it in with polynomials is because we don't have anything. It's a nice smooth curve, so we don't have any holes in the graph. There's no, we'll learn about jumps. There's no asymptotes or anything like that. So polynomials, we can just plug in the value because the limit will end up being the actual value at that point. Same thing for rational functions, as long as the denominator is not 0. So basically what I'm telling you is if you see a limit, try to plug it in first. And if that doesn't work, then there are other things that we can do. So plug in the -2 here. So plug it into the numerator and denominator. So we get -1 over 4. And that's the limit.
You go over 4a.
Can I go over what?
We haven't done that yet,
I know, but I
Okay.
was just looking at it.
but we're getting there.
Okay, to determine the limit by substitution, and then we can support graphically. So starting with this one, again, this is a polynomial function. So we can just plug in 2.
You get 4.
So you get 2 to the third minus 2 times 2. So we get 4. This one, if we plug in 1 of the things we want to check for is just to make sure that the denominator does not end up being 0. We're fine in this case. So just plug it in. We have 2 minus 7 plus 4 plus 5.
If it did equal 0, would the limit not exist?
Possibly. So I'll explain that then in a minute. We have some down here. Okay, so what do we get in the numerator?
1.
Four.
Oh, yeah.
Oh, we get 4 over 4, which is 1. Support graphically. If we have more time, which we can look at that on Monday, you can graph it on your calculator like we did the sine x over x and look at values that are getting closer to 2 for this graph and values that are getting closer to 1 for this one. We could do that one, but I want to do these 2 examples quickly.
Is it?
Okay, so let's just look at algebraically first. If I were to plug this in, so if I plug in 2, that makes the denominator undefined, right? So it makes the denominator 0. So I am going to see if this will factor. So the numerator and denominator, well, the numerator is t minus 2 and t minus 1. And the denominator is t minus 2, t plus 2.
Oh, so you have.
Okay, so
Oh.
now, here's an important, one of the things I keep telling you is that, remember, the limit, we don't care what happens at the actual value, we just want to look closer and closer. So t is approaching 2, right? So I can cancel the t minus 2 over the t minus 2, because I know it's not going to be 0. So one of the rules that
So then if you filled in the t, the denominator would be 0.
so now we don't need to worry about the denominator coming out to 0. So now I can look at the limit as t approaches 2 of just t minus 1 over t plus 2, so I get 1/4. We're all right with that?
Wait, so that's
So
where you
this
plug-
is the
that's where you
limit.
plug in the 2 right there.
Yeah, you plug in the 2 in the top and the bottom, and you get 1/4. Okay, the next one, this will be the last thing we do. This is a complex fraction. So again, obviously if we try to plug in 0, we get undefined. So I want to try to figure out how can I simplify this.
Can you flip it? maybe?
Oh, multiply everything by x.
Oh yeah, multiply everything by x. Yeah.
X?
No, because then you see the x squared on the bottom, and if you still plug in 0, you get 0.
And
Multiply by denominator.
denominator.
This is 2 plus
Okay.
x, so you multiply this all by x.
Let's multiply. Let's try to simplify that complex fraction. So in order to do that, we'll find a common denominator. Don't worry about the x on the bottom for right now. Just do the top 2.
What? What's the 2 plus x?
The 2 plus x is the denominator that's on the left, so you multiply it to the right fraction, and then 2.
Oh, I see, I see.
denominator from the right.
Now, notice when I combine these, because we have a common denominator, I'll end up with a 2 minus 2, so the 2's cancel, and then a minus x. Are we okay with that? So I have a minus x over 2 times 2, 2 times 2 plus x.
All divided by x.
Now, instead of dividing by x again, remember I can multiply by a reciprocal, right? Dividing by x is the same thing as multiplying by 1 over x. Why does that help me to write it that way?
Cancels out x.
Because
Yeah,
then the
that
denominator
alone
will be
is bottom.
different.
So then it cancels out the x here and here. And the top here, bottom here. Remember, dividing by x is the same thing as multiplying by 1 over x. That allows us to cancel. So now I have the limit as x approaches 0 of negative 1 over.
And then it's negative.
Now can I plug in 0? Yes.
Oh, you plug in 0 now.
Yeah, and then we get negative 1/4.
Yeah, can you go, I'm confused. I think when you skip a step, I know, but I'm confused about
I
like,
skipped a step for
sometimes you get negative x on top. You multiply.
2 minus 2 minus x. I distributed the minus sign. See this here? This would be 2 minus 2 minus x which gave us the negative x there.
But on the bottom, wouldn't it, which gets 0? Isn't it 2? 2 plus x minus 2
Mm-mm.